Okay, lesson 1.15B, limits at infinity. Find the following limits. Okay, so problem number 6, limit as x approaches infinity of this rational function. So you have a third degree polynomial for the numerator and a third degree polynomial for the denominator. So at infinity, as x gets bigger and bigger and bigger, the -2 and the 5 become almost inconsequential to how big, say, even x squared becomes, or this x becomes. And then the x squared at infinity becomes almost relatively small compared to how big this one becomes. Same here, the cubic with the first degree term here. So at infinity, this becomes almost inconsequential. This one becomes so now it's a race between 4x to the third divided by 2x to the third. So these become constants. X to the third over x to the third becomes just a 1. So the answer turns out to be the coefficients, the leading coefficients of the top over the leading coefficient of the bottom, 4 over 2, and the limit is 2 at infinity. Okay? Number 7, limit at infinity. Let's rewrite this a little bit better. Limit as x approaches infinity of -x squared plus 1 over x to the third minus x plus 1 at infinity. This becomes almost inconsequential right there and right there. We're left off with -x squared over x to the third. So the bottom has a bigger power than the top. We can actually kind of cancel that out, and it will become limit as x approaches infinity of -1 over x. So what does -1 over x look? What does that look like on a graph? So basically, if you want to think about what -1 over x looks like, it would be the rational function reflected about the x-axis. So it's going to look like this. So the limit as x approaches infinity, meaning we go closer, no, we're going to infinity, it will get closer and closer to 0 from the bottom. So the limit will be 0. So another way of looking at it is that x gets really big, you will get -1 over, say, 1 million or whatever, a billion. It approaches 0. So it's going to be -0.00001. And as you get bigger and bigger, it'll be closer and closer to 0. So the answer will be 0 here. Number 8, the limit as x approaches infinity. Again, these numbers become inconsequential as x gets bigger and bigger all the way to infinity. For the bottom, the constant becomes nothing almost. There we go. Then we can rewrite this as limit as x approaches infinity. So you're going to get 4x to the third power is 64 over x to the third. Then we got the bottom will be 2x to the power of 2. That's going to be 4x squared. And then multiply that by x to the power of 1 is x. So we can keep going, limit as x approaches infinity. this would be 64 divided by 4 is 16 times, and then you got an x to the third over x to the third, which again cancels out, and the limit will be 16 at infinity. Problem number 9. Limit as t approaches infinity of this function. Well, we got to figure out which one is the higher power here on top. So let's rewrite this as limit as t approaches infinity. T approaches infinity. The top one, we can rewrite this right here as t times t to the 1/2. That's what this is. Then we're going to go t to the 1 power becomes 2 over 2 is 1. And then when we have the same base, we add the powers. So that would be t to the 3/2. So let's put this in the front. So we're going to have negative t to the 3/2 power plus t. And the bottom, let's leave it alone as 2t to the 3/2 power plus 3t minus 5. At infinity, relatively speaking, t becomes almost nothing compared to that negative t to the t to the 3/2 power. For the bottom, this becomes relatively, it almost disappears in relative growth to the other one at infinity. And so now we have negative t to the 3/2 divided by 2 to the 3 t to the 3/2. And those cancel out, so we're going to get limit as t approaches infinity of negative 1 over 2. And that should be the answer. Well, the limit will be negative 1 over 2. Number 10. Here's where we have a problem with the way I just did the other ones. Why? Because if I do say this, limit as x approaches infinity of this function, and I continue on saying that, relatively speaking, 9x squared is going to grow way bigger compared to x, that I'm going to ignore x. And then I proceed to continue on the way I was doing the other problems, limit x approaches infinity. And so now I have a square root of 9x squared. The square root of 9 will be 3. And the square root of x squared is the absolute value of x minus 3x. We're going to positive infinity. So we only care about the positive x, not the negative x of this part. So we're going to do the limit as x approaches infinity of 3x minus 3x of this thing. Well, the limit as x approaches infinity of 3x minus 3x, the answer seems to be that the answer would be 0. But that would be incorrect, because the limit is not 0. So what is the correct answer to this? And what procedure should you use when it comes to a square root of a quadratic of minus some linear function? Is that you need to multiply by the conjugate. So if you do multiply by the conjugate, 9x squared plus x plus 3x over square root of 9x squared plus x plus 3x, and we FOIL out the top, we're going to get lim as x approaches infinity, and then we're going to get on top 9x squared plus x minus 9x squared over, leave the bottom alone, 9x squared plus x plus 3x. 3x. On the top, we can cancel off 9x squared with 9x squared, and we're going to be left out with limit as x approaches infinity of x over the square root of 9x squared plus x plus 3x. Now, why is this going to work? And I apply the same idea of that at infinity, x becomes arbitrarily small compared to this. So then I am going to go ahead and do it now and say limit as x approaches infinity of x over the square root of 9x squared at positive infinity will just be 3x. And then we do have a 3x after this right here. And as we continue, we're going to get limit as x approaches infinity of x over 6x. And now we can cancel out those x's. And the limit will be 1/6. And this is the correct answer. I have to look deeper into why this is true, that the first method did not work, and the second method does in fact give you the correct answer. And I will get back to you guys on that. Okay, we're done.